All right, so let's get started. Let's start with chapter 2 today. I put up a video for the remainder of chapter 1, which covered the concepts of parallax and um, uh, angular diameter. Okay, so in this chapter, we are going to talk mostly about the history of astronomy. And towards the end of this chapter, we are going to start getting into the scientific part of this course. So in chapters, end of this chapter, we'll talk a little bit about science. And then chapters 3, 4, and 5, we'll talk about the scientific background necessary for astronomy. And then from chapter 6, we'll really start with the astronomy. All right, so uh, ancient astronomy. So astronomy is the oldest science. It's been around ever since we have been we have existed as human beings. Our ancestors have always looked up at the skies and wondered what is going on with all these amazing and wonderful spots of light in the sky. So astronomy is the ancient science. Is the most ancient of all the sciences, is what I mean. And ancient civilizations used astronomy in many different ways. So one example is they would use astronomy to determine the time of the day. And so basic idea is that if you plant a stick on the ground and keep an eye on the shadow of the stick, then you can tell the time of the day by just watching the shadow of the stick. So when the sun is low in the sky, the stick will have a longer shadow. And if the sun is high up in the sky, the shadow of the stick will be smaller, and so on. So by just keeping track of the shadow of a stick or a large object planted in the ground, you can keep track of time. So there are many examples of devices like this. One spectacular example is the Egyptian obelisk. Let me see if I have a picture linked over here. Might show up. Yeah, so here it is. It was found in Egypt, but Europeans moved it to Europe. I believe it's in Italy right now. So this is a device which is similar to that. You can which works on the same principle, that you can tell the time of the day by looking at it, by looking at the shadow. Then ancient civilizations would also mark the seasons and the sun's position on special days. So they would build devices that would mark the seasons and the sun's position on special days. Um, One example is Stonehenge, which you might have heard of. It's this collection of structures that was found in England, very old collection of structures found in England. And researchers have found that there is a particular order to the way those stone structures are situated. And the sun, for example, on the day of the summer solstice, the sun rises in between two of the stones, and so on. Another example is uh, this wheel. I mean, it's called the medicine wheel, I think, which was found in Wyoming, I believe. And it's a collection of rocks which are arranged in a very particular way. And the way these rocks are arranged, it lines up with the positions of the sun and the moon on special dates. Um, there is this sun dagger, which is okay. I believe watch this stupid ad. Okay, all right. So let me, oops, let me just change the setting here. All right. So this was found in New Mexico. And this was actually discovered pretty late, like in the 1970s. Somebody noticed that on the day of the summer solstice, I've forgotten exactly what day it is, maybe the summer solstice, the sun forms a sliver of light from the sun forms something that looks like a dagger, which goes through the center of this, of this pattern. So I'll let you watch this. So this is the sun dagger, and it happens only on one day of the year. It's pretty amazing. So this could have been used to mark the day of the summer solstice. So because that's the only one day that the sunlight will do this. Um, oops. So ancient civilizations used astronomy in various different ways. And
this is how people tell time. This is how people understand how to be in time.
Turn off this video here.
We're
all right. So ancient civilizations used astronomy in various ways. One more interesting example of the way astronomy was used by ancient civilizations was that in central Nigeria, the people figured out, and it's not really known when this was figured out, but it's been known for a very, very long time, or who figured this out. But people in Africa figured out that by looking at the orientation of the horns of the crescent moon, you can predict rainfall. Because as it turns out, in Africa, in central Nigeria, when the moon is more or less in this, when the crescent moon is more or less in this configuration, um, then you have a lot of rainfall. So that happens at the time of the year when they have a lot of rainfall. So this graph shows you the amount of rainfall that you get. And when the moon is in a different configuration, then you don't get that much rainfall. So by looking at the moon, they were able to get a heads up on how much rainfall is going to happen around that time. So they were able to predict the weather with reasonable accuracy. So there are many, many other examples, but these are just a few examples of how astronomy was used by ancient civilizations. Now, the Chinese, ancient Chinese kept really detailed records of the skies. Um, the reason that they kept such detailed records was because they were particularly interested in omens, or objects which showed up in the sky that were out of the ordinary, because they believed that these objects would play a role in their lives. So these objects would be omens. So if they saw something new in the sky, that might mean that something important or something significant is about to happen. So what would be something that's new in the sky? The most common example would be comets. So we're going to learn about comets in chapter 14. So comets are objects um, which are visible when they are close to the Earth. So they basically orbit the sun in highly elliptical orbits. And so sometimes they're visible from the Earth. And so when they're visible from the Earth, they're pretty hard not to notice, and they have a very peculiar shape. We're going to learn all this later on. And then they're visible from the Earth for a while, and then they just go away. So you can't see them again. So comets are one thing that the ancient Chinese would have noticed when they were watching the skies. And so they made detailed records of all the comets that they saw. And another thing that they noticed, though it's not as common, would be supernovas. So a supernova is basically a very powerful explosion. It's probably the most violent event that can happen that ever happens in the entire universe. So a supernova happens when a large star collapses and dies. So when a very large star, by large star I mean much larger than the sun, when a very large star collapses, and stars have a definite life cycle. So at the end of their life cycle, they die. So when a very large star dies, there is a very, 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 very powerful explosion that happens. And that explosion is so incredibly powerful. Let me just give you an idea of how powerful that explosion is. So the sun, we know that the sun gives off an enormous amount of energy, right? An enormous, enormous, enormous amount of energy. And we only intercept a small part of that energy, because the sun is like this. This is the sun, let's say, and the sun's energy is going off in every direction, enormous amount of energy. But we are our size as the this is the Earth. The Earth is very, 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 very tiny in comparison to the sun, and so the Earth only intercepts a very small amount of energy that the sun is putting out. Only this much energy is all that the Earth is intercepting, and that is what powers everything on the Earth, right? So the sun gives off an enormous amount of energy, and how much energy does a supernova explosion give off? Well, a supernova explosion, when a star explodes, it gives off an amount of energy which is 10 to the power of 44 joules. We learned what scientific notation is in last week. So you know that 10 to the power of 44 would mean 1 followed by 44 zeros, and joule is a unit of energy. So 10 to the power of 44 joules of energy is given off in a supernova explosion. How does that compare with the amount of energy that's put out by the sun? Well, if you calculate the total amount of energy that's put out by the sun over a period of 10 billion years, which is the lifetime of the sun. The sun is only going to, a star like the sun will only last for 10 billion years, and we are at about 5 billion years right now. So 4.5 billion years right now. So the sun only has about 5.5 billion years left. But if you calculate the total amount of energy that the sun puts out over its entire 10 billion year life, that comes to 10 to the power of 44 joules. So the amount of energy that a supernova explosion gives off in a matter of 1 or 2 weeks is equal to the total amount of energy that the sun puts out in its entire 10 billion year lifetime. So that gives you an idea that a supernova explosion is a very, 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 very powerful explosion. When a supernova explosion happens in a distant galaxy, that one star in that galaxy can outshine the entire 100 billion stars in that galaxy. That one star is brighter than the combined brightness of 100 billion stars in that galaxy. So a supernova explosion is a very, very powerful explosion. And when that happens, it appears that you see this light in the sky that shows up out of nowhere if the supernova explosion is relatively close by. And that is something like this that happened in the year 1054. There was a supernova explosion which was relatively close by. And at that time, the Chinese astronomers noted that there was a guest star in the sky. So they saw this new object in the sky, which they say was so bright that it was visible during the daytime for a few months. And so the Chinese astronomers took detailed records of this supernova explosion, which happened in 1054, in AD 1054. In fact, the Chinese were not the only people that saw it. So this explosion was seen by people all over the world. There are cave drawings from North American Indian cave drawings from around that time, which show this bright object in the sky, right? Other civilizations, pretty much every civilization in the world noticed it, but the Chinese kept very detailed records of their observations. And here is one example of that. This is this is this inscription is an ancient Chinese record of the 1054 supernova. In fact, the highlighted portions over here, which if you can read Chinese, which I cannot, talk about an object being seen in the sky, which is so bright, a new object being visible in the sky, which is so bright that it's visible during the daytime, and how it was visible in the sky for a month or so. So the ancient Chinese took detailed records of, maintained detailed records of the sky, with particular emphasis on newer things that were seen in the sky. All right. Okay. Now, Islamic astronomy. So Greece, ancient Greece was a powerhouse of intellectual activity for a while. But then the Dark Ages began. If you've studied the history of Europe, the Dark Ages began. And so at that time, there was a period of intellectual decline. And because the European countries were mostly busy fighting wars and stuff like that. So at that time, um, Islamic astronomy flourished. So Islamic astronomers or Islamic scholars started studying, translating, and studying the works of the of the great Greek scholars, and then they preserved that work, and they also augmented that knowledge, and these Islamic astronomers made tremendous progress in astronomy and mathematics and science in general. So many astronomical terms such as zenith, which we've talked about, which I discussed at the end of the last chapter, azimuth, and then the names of several stars such as Aldebaran, Betelgeuse. These all come from Islamic astronomy. So many stars have strange sounding names to us because these names are based in Arabic. And also many mathematical terms are also come from Arabic. Um, I believe algebra comes from al-jabr or something like that. I don't remember exactly. It basically has an Arabic root. So so Islamic astronomers developed many mathematical techniques as well to solve practical problems. All right. Now, uh, ancient astronomers, when they looked up at the sky, they observed the things that they saw were the sun, the moon, the stars, and 5 planets: Mercury, Venus, Mars, Jupiter, and Saturn. Um, do you know why I am only mentioning 5 planets? What about the other planets, Uranus and Neptune? Ashley, do you have any?
I could only imagine that maybe they didn't have the technology to see.
Yes.
Okay.
Yes, that's right. So Uranus and Neptune are very difficult to see. It's not impossible to see Uranus with the naked eye, but you have to be very, very observant, and you have to know where to look. Neptune is practically impossible to see without some binoculars or a telescope. So in those days, they only knew about these planets: Mercury, Venus, Mars, Jupiter, and Saturn. All right. Now, the sun and the moon and the stars have simple movements in the sky. So the sun rises in the east, sets in the west. The moon also does something similar. And the stars form these constellations which really don't change. They only change from season to season. And we discussed in the last chapter why that happens. Like, they only change over the course of a year, but it's fairly predictable. Like, you'll see Orion in December, and then Orion will gradually disappear, but it will come back again in December. You'll see it again. So the sun, the moon, and the stars, to them, had simple motions. So they fully understood that. It wasn't complicated. What they absolutely did not understand, and what completely puzzled the heck out of them, was the planets. So the planets had very strange motions, which they absolutely couldn't understand at all. So first of all, the planets seem to move with respect to the fixed stars. So if you are looking at any planet, say Jupiter, in the sky tonight, and then tomorrow night you will find that it has slightly changed position, and then the day after that you'll find that it's all again changed position in the sky relative to the stars. So the planets move around with respect to the stars. The Another thing is that the planets seem to change brightness. So today Jupiter or Mars might be bright, but say 6 months from now it might be a lot dimmer. So the brightness of the planets changes with time. And then another thing is, we just mentioned how the planets move across the sky I mean, you won't see it moving like an aeroplane moves across the sky because they're very far away, obviously. But over a period of a few days, if you carefully track the motion of a planet, I mean, track the position of a planet, you'll see that it is changing position. So not only do the planets change position, they also change speed. So sometimes you might find that a planet has moved quite a bit across the sky over the period of a month, but then another time you might find that it's really not moving that fast. It's moving quite slowly, or it's hardly changed position at all over this month. So the speed at which they move across the sky is different. And another thing which really puzzled the ancient astronomers was that planets seem to undergo retrograde motion, which means that sometimes a planet might appear to be, so most of the time you'll see, if you keep track of Mars, for example, most of the time you'll see that it's moving in one particular direction across the sky, but then you might find that it's slowing down, and then very surprisingly, it starts moving backwards. And so it moves backwards for a while, and then again it starts moving forward. So this is called retrograde motion, when a planet seems to move opposite the direction in which it normally moves. So that is retrograde motion. And your book has this example. Suppose you are, oops, okay. Okay, so suppose you are keeping track of Mars, um, and on the 1st of April, okay, 1st of November, Mars is over here. So you're keeping track of Mars in the sky. You can easily use these stars. And so there are some stars, and you can see the constellation Leo and the constellation Cancer. So these stars will not change position. So you can easily use them as a reference to keep track of the positions of the planets. So in November, you'll see Mars over there, the place where I drew a circle. December, you will see that Mars has changed position quite a bit, and now it's over here. January, you will see that Mars has moved over here, left of the constellation Leo. So you might think that, okay, I get it. Mars kind of wants to move in this direction, and that's what it's doing. But then in February, if you look for Mars, you'll be very surprised to find that it's actually moved backwards, and it's over here. March, you'll find that it's been moving really fast in the backward direction. And in 1 month, it's covered quite a lot of distance in the sky, and it's over here. So you'll think that, okay, so it's changed its mind and now it wants to move in the opposite direction. But in April, you will find that it's again changed its mind. It now wants to keep moving in the original direction in which it was moving. And then May and June, it just keeps moving in that same direction. So it will keep doing this. So then again, you keep following it for a while. After a few months, you might see that again, it's beginning to slow down, and it will just start coming back for a while, and then it will go forward. So this kind of motion is called retrograde motion, and all the planets seem to have retrograde motion. So for all of these reasons, ancient astronomers or our ancestors were absolutely puzzled by the motion of the planets. In fact, the name planet comes from a Greek word, planeteer, I believe. Planeteer, if I remember correctly. Probably, don't quote me on this, which basically means wanderer. That's where the word planet comes from. Okay. Now, whenever we have, as human beings, whenever we see something that we don't understand, our instinct is to try to understand it. And if we can't understand it, we try to give it a lot of meaning, right? And we imagine that maybe it has some deep significance if we can't understand it clearly. So we think that it's probably some power higher than us, and it has some deep significance it might have some deep significance in our lives. And that is exactly what happened with these planets. So people started believing that these mysterious planets, the motion of these mysterious planets, is somehow connected with our lives. And so they started believing that, okay, if Mars is in this particular constellation, is in the vicinity of this particular constellation, that's a good thing. So maybe there'll be good luck for me. Maybe my crops will produce a bumper harvest or something like that. And if Mars is in that part of the sky, bad things happened the last time it was in that part of the sky. So maybe Mars being in that part of the sky is really bad, and so I should plan accordingly, be ready for bad things to happen when Mars is in that part of the sky. So over a period of centuries and millennia, people started associating the position of the planets with they started giving significance to the positions of the planets, and imagining that that had something to do with our lives. And so that led to the whole field of astrology, which many people still believe, that the positions of the planets in the sky plays a role in our lives. So there was a tremendous amount of interest in trying to understand the positions of the planets, because as I just said, people believe that it's very important. They play a role in our lives. So they really wanted a way of understanding, where is Jupiter going to be 6 months from now? Or where is Mars going to be 6 months from now or tomorrow? Just because Mars being in a particular part of the sky might have some great significance in my life. So that's why people were really curious, and they really wanted to understand how the planets move. And they wanted a way to be able to predict where the planets would be, right? So that played a very important role in our understanding of astronomy. Now, okay, so let's talk about Plato very briefly. So Plato is a very famous philosopher from ancient times, and he wrote about moral responsibility, ethics, nature of reality, civil government, and all that stuff. So if you've taken a philosophy course, you've definitely heard of him. We are going to talk about Aristotle, who was a student of Plato, and he lived from 384 to 322 BC. And he also wrote on a very wide variety of topics. So Aristotle was a very, very intelligent person, and he did a lot of scientific exploration, particularly in biology. I believe among many of the things that he discovered, he realized that that dolphins are mammals, and so they should not be classified as fish. He also made many discoveries regarding plants. Um, so uh, now, as we will see in a lot of detail in today's lecture, Aristotle also made a lot of, tried to understand the physical world and astronomy. But most of the things that he figured out concerning the physical world were completely wrong. And that is because neither Plato nor Aristotle had the tools of modern science available to them, and they did not have the correct framework for scientific thinking. So in chapter 1, we talked about the scientific process, uh, and how scientists approach a problem through observations and then predictions, then observations and then making hypotheses and then making predictions, testing those predictions with further observations and so on. So that is the current way of understanding science, the scientific method, but that was not available at the time of Aristotle and Plato. So it's not surprising that almost everything that they figured out, particularly Aristotle, almost everything that Aristotle figured out with respect to the physical world was completely wrong. Okay, so Aristotle came up with, he didn't really come up with it, he basically combined ideas that existed with his own thoughts, and he basically synthesized this model of the world. So what people really wanted was a deeper understanding of what's going on with the Earth and all these planets and stars. So what's the big picture? Like what's going on? So they had no idea. So they just knew that you have all these things in the sky, and the sun and the moon and the stars seem to have simple motions, and then there are these spots of light which have these crazy, almost random like behavior, not random but crazy behavior, which they didn't understand. So they wanted a big picture of understanding of what was going on in the sky, right? So Aristotle came up with the geocentric model of the universe. What does geocentric mean? Geocentric means that Earth is at the center of the universe. So that's why it's called geocentric. So in this model, the Earth is located at the very center of the universe, and everything in the heavens, stars, planets, sun, moon, everything orbits the Earth in uniform circular motion. So what does uniform circular motion mean? It means that if something is orbiting the Earth, it is moving with a fixed speed in a perfect circle. So that is what uniform circular motion means. So fixed speed in a perfect circle. So Aristotle believed that the Earth is at the center of the cosmos. So everything The entire cosmos revolves around the Earth, literally revolves around the Earth. The Earth is at the center, and all the stars and the sun and the moon and the planets uh, orbit the Earth in perfect circles at a fixed speed. And so that's uniform circular motion. He also believed that the sun and the moon and the planets are perfect spherical orbs of light. So they're these perfect spherical orbs, these spheres. Okay, now at the time of Aristotle, what people meant by the universe was basically the solar system, the sun and the earth and the moon and the planets. So that is really what they cared about. They were not too concerned with the stars because they believed that the stars are are separate. So we talked about the celestial sphere in the last chapter. So the celestial sphere is when you look up at the sky, you can imagine that that all the stars and constellations are painted on this surface, on this dome, on this sphere which surrounds the Earth. And so that imaginary sphere is called the celestial sphere. So in ancient times, people believed that the stars and all the constellations and all that, they are sort of painted around that celestial sphere, um, like a piece of artwork. And so they didn't really care much about those, the stars. So what they really cared about was the sun and the moon and the planets, right? And so Aristotle believed that the center of the universe was the Earth, and the sun and the moon and the planets orbited the Earth in perfect circles, and also that the sun and the moon and the planets were perfect spheres, perfect orbs of light, which orbited the Earth. That makes sense? Any questions about that?
I think I should read more about it, but I understand what you're saying.
Okay. All right. Now, this was the model that Aristotle came up with. Now, why would you care about a model? So what was the point of coming up with this model? The point was that with this model, you sort of have an understanding of what the planets are doing. And so then you can make predictions on where a planet is going to be in the sky, right? So based on this model, it was possible to make predictions to say that, okay, so at the time of winter of this year, Jupiter should be seen in this part of the sky, in this constellation, or Mars should be seen in that constellation, and so on. So it was possible to make these predictions based on this geocentric model, though the geocentric model we know is completely wrong. It's certainly not true that the Earth is the center of the cosmos. So we know that now, but they didn't. At the time of Aristotle, they didn't. So they were able to make predictions of where the planets are going to be with reasonable accuracy, even though the model was wrong. Now, one thing that this model could not explain was the retrograde motion of the planets. So if you have, in the incorrect geocentric model, so in the geocentric model, which is wrong, I'll just put wrong over here. You have the Earth at the center, right? And then the sun and the moon and all the planets like Mercury, Venus. So I'll just write Venus, Mars. This is moon. So these are all orbiting the Earth in circles. So this is the geocentric model. So these lines are just the orbits of these planets. So if everything is orbiting the Earth with a fixed speed, then why do some of the planets appear to move backwards for a while? So how do you explain this retrograde motion? So it's not possible to explain the retrograde motion based on the geocentric model, right? And so even though at the time of Aristotle, this geocentric model could be used to build up almanacs and tables of where you're going to find the sun and the moon and the earth, and the planets at different times of the year. Since the model is wrong, after a while, these predictions started to all be wrong. So maybe 100 years after Aristotle came up with these, Aristotle and people of his time came up with these detailed tables of where you should see the different planets at different times of the year. After a few years, or maybe even 100 years or so, people started noticing that the predictions of these tables are wrong. And so they knew that something must be wrong about this model because it's not giving the right answer after a while uh, regarding the positions of the planets. And also, it was not quite able to explain why the planets have retrograde motion, right? So that problem was solved by Ptolemy. So Ptolemy is spelled like this, but it's pronounced as Tolemee. That's kind of how you pronounce this name. So Ptolemy, 5 centuries after Aristotle, realized that there must be something wrong with the original geocentric model that Aristotle put up, that Aristotle came up with. And it needs to be upgraded, and maybe it's missing some elements. It was clearly missing something because it was not able to explain the retrograde motion of the planets. So Ptolemy came up with what he thought was an improvement to the geocentric model. So he said that um, this is, instead of this, the Earth being at the center and all the planets and the sun and the moon orbiting the Earth in perfect circles, maybe what they're doing is a little more complicated. So the Earth is still at the center. So the Ptolemaic model is still the geocentric model. But Ptolemy said, and I'll just take one example, let's say Jupiter. I'll just take one example of a planet. So instead of going around in a perfect circle around the Earth like this, Ptolemy suggested that maybe Jupiter does circles within circles. So instead of doing this, maybe Jupiter is doing something like this. I mean, it's basically going around in a circle, smaller circle, as it traverses the larger circle, right? So it's kind of doing something like this. So it's trying to go around in a smaller circle, and at the same time, it's traversing the bigger circle. So there's a nicer picture over here. So, so here is, if you look at this Saturn, for example. So Saturn is going around in this big circle, big orbit around the Earth, but at the same time, it's also describing a smaller circle as it goes around this big circle, right? So this smaller circle is called an epicycle. And why do we need to introduce the idea of an epicycle? Why did Ptolemy come up with the idea of an epicycle? Because it explains, it seems to be a simple explanation for why there is retrograde motion. Because when a planet, so if a planet is also describing smaller circles as it's going around in a bigger circle, then when observed from the Earth, which is believed to be at the center of everything, sometimes the planet might be appearing to move backwards. So for example, let's look at Jupiter over here. So remember that in this model, Jupiter is executing a large circle, and while executing the large circle, it's also executing smaller circles, right? While executing the large circle. So the path of Jupiter as seen from the Earth seems to be this dashed line. So it's like this, because it's doing both. It's doing the bigger circle and it's also doing the smaller circle. But you can see that sometimes from the Earth, it would seem like it's moving backwards. So it's moving forward now, but now it would seem to be moving backwards for a while, and then again it would move forward. So Ptolemy explained the retrograde motion of the planets successfully by assuming that the planets describe smaller circles within the larger circle that they're describing around the Earth, that they're executing around the Earth. So you can see that this model is very complicated now. So not only are the planets executing circles around the Earth, they're also executing smaller circles within the bigger circle that they're tracing out. Now, by adjusting the sizes of these circles, Ptolemy and people of his time were able to make the predictions of this model accurate again. So I told you that this model had sort of was not giving the right answers. But by adjusting these, the sizes of these epicycles, Ptolemy was able to again make this model more accurate. So it was able to again give correct predictions. It's a wrong model though, but it was able to give correct predictions. And so it was believed that Ptolemy is right. So what Aristotle must have missed is that the planets don't just go around in circles, they execute smaller circles within the larger circles. Now, one other thing is that by adjusting these epicycles, actually it turns out that you can make this model agree with experimental data um, as much as you want. In fact, later on, people figured out that Ptolemy's model, which at the time of Ptolemy was giving correct answers on where on making correct predictions on the positions of the stars and the planets, but even that started giving wrong answers after a while, because after all, the model is completely wrong, right? So you can't expect it to always give you the right answer. You might fine tune it a little bit, and then it might give you correct answers for a while, but since it's inherently wrong, you wouldn't expect it to always give you correct answers. So when after Ptolemy, 100 years or so after Ptolemy, when people realized that, oh, Ptolemy's model also is giving the wrong answers, then they figured that maybe there are more epicycles than Ptolemy realized. So people started thinking that there are circles within circles within circles. So maybe the true path of Jupiter is actually, it's doing this blue thing, but also while it's doing the blue thing, it's also tracing out even smaller circles like this. So, so this is the real path of Jupiter. Circles, 3 layers of circles. And then they also added more layers of circles. The advantage of adding more circles is that you can mess around with the model, and then you can make it give the correct answers again, right? So this model over the centuries started getting tremendously complicated. So you have the Earth, you have everything orbiting the Earth, and the motions, and these orbits are very complicated because they are not just circular orbits, they're circles within circles within circles, however many circles have been introduced up till that point. So the Ptolemy's model, which is also called the Ptolemaic model, was able to successfully explain the retrograde motion of the planets. So and so that was a big improvement over Aristotle's model. But and it was at first, it was also able to explain the motions of the planets well, but as the centuries passed, it got more and more inaccurate, and so people had to keep on making this even more complicated in order to get correct answers. So and they made it more complicated by introducing more and more circles within circles. Okay, so that is the Ptolemaic model. So we talked about Aristotle's original geocentric model, and then we talked about Ptolemy's changes to the geocentric model. And we saw that the Ptolemaic model was able to explain the retrograde motion of the planets. So is everything, any questions so far?
No, thank you.
Okay. All right. Now, the why did people, so if we study the geocentric model now, it all seems really silly. So I mean, it seems ridiculously silly, the Earth being at the center, and then everything, the sun particularly orbiting the Earth. It's silly to the point of being hilarious at this point, but people believed it very, very strongly. So why did people believe in a model which to us seems really silly? There are many reasons why people believed in the geocentric model, and people believed in it for a good 14 centuries. So it's not just something that was a fad that lasted for a month or so. It's something that people believed in very firmly for a period of 14 centuries almost. So why did people believe in the geocentric model? Well, in those days, if you just asked a common person on the street, why do you believe in the geocentric model? Suppose you're a time traveler and you go, you somehow get into a time machine, go back to the time of Ptolemy or earlier, and then you tell a person, a random person on the street that, like what you guys believe, that the Earth is at the center of the universe and everything revolves around the Earth, is complete nonsense. What actually happens is the sun is the center of the solar system, and everything, including the Earth, actually orbits the sun. They would not believe you at all. They would think that you are completely crazy for saying that. So some of the reasons why people believed in the geocentric model was that it doesn't feel like the Earth is moving. So in those days, people's only experience with motion, and particularly fast motion, would be riding a horse, right? So that's the fastest mode of travel. And so when you ride a horse, there's this wind which blows in the opposite direction, and you know very well that you're moving fast because you can see this wind blowing in the opposite direction. So people at that time would say that the Earth cannot possibly be moving around the sun because there is no strong wind which is blowing in the opposite direction. So how can you possibly say that the Earth is moving? There would be a very strong wind blowing in the opposite direction. Another thing that they would say is that how can the sun be the center of the whole universe? Because if you drop an object, it always falls towards the earth, right? So the earth seems to be the center of everything. If you drop any object, it always falls towards the earth. If you drop an object, it does not fly off towards the sun. So clearly, the sun is not the center of everything. The earth is the center of everything. And so objects which are dropped fall towards the earth and not the sun. And so it seems plausible, at least at the level of knowledge that they had at that time, it seems plausible to say that the earth is really the center of everything in the cosmos, right? Now, these were not that important reasons. The most important reason was this one. So if you asked a really smart person, a really educated, knowledgeable person at that time, why they believe in the geocentric model, they would tell you that it's because the stars don't show any parallax. Now, in the video that I put up discussing the last part of chapter 1, I explained the concept of parallax. It's a very important concept. So if you haven't watched that video, please make sure to watch it. It's also something that will definitely be on the next timed quiz and on exams. But very briefly, what is parallax? Parallax is something that you can demonstrate right away if you just close one eye and look at whatever is in front of you, and then you open this eye and close this one, and then again look at the world. And if you do this quickly, you'll see that there's a slight change in perspective. So if you're looking from this eye, it looks a certain way, but if you're looking from this eye, it looks slightly different. You can try it yourself. Just close one eye and then open it and look through the other eye. So that slight shift of perspective is parallax. And so very briefly, and I explained this in a lot of detail in my in the video that I put up. Suppose you have a star or any object over here, any star or something, maybe a close nearby star, and you are actually yeah, okay, nearby star, that's fine. And here is the sun, and the Earth is orbiting the sun in a circular orbit like this, almost circular orbit like this. So when the Earth is over here, let's call this position A. When the Earth is in position A and you are on the Earth, in my diagram, you're bigger than the Earth, but that's all right. So you're on the Earth and you're looking up at this particular star. Let's say that there are some very, very distant stars. So there's a bunch of very distant stars over here. And let's say that there's a bunch of very distant stars over here. So if you are looking at the star, let's call this star S, so it's easy to refer to them. If you're looking at star S from when the Earth is in position A, then and let's say you take a photograph of the sky with star S, you will see star S in the vicinity of this group of stars. 6 months later, when the Earth is over here, and you again look at the same star in the sky and take a picture of it, you will see that it shows up in the vicinity of this group of stars, right? So the position of star S in your photograph will change by a small amount. If you photograph the star in a certain time and then photograph it 6 months later when the Earth is in a completely different location, you will see that the position of the apparent position of that star is slightly different. And that is not because the star has changed position at all. It's simply because you, the observer, have changed position. One time you're looking at the star from over here, the other time you're looking at the star from over here. Now, from that subtle shift in position of that star, I discussed in my video that it's possible to measure this angle right here. And this angle is called the parallax angle. And if you know the parallax angle, and if you also know this distance, this is called the baseline distance. So if you know the parallax angle and the baseline distance, you can plug them into a simple formula and calculate the distance to that star. And so that is one way in which you can find the distance out to a different objects. And we discussed, this is just a review of what I discussed in a lot more detail in my video that I put up. But that is the phenomenon of parallax. So the point is that in January, if you're watching a particular star and that star happens to be close by, then 6 months later in June, that star will, since you're watching it from a different location, that star will have seem to have slightly changed position in the sky, right? So that means you will see a parallax effect on that particular star because your vantage is different, right? You don't have to wait for 6 months. You could, in principle, see a parallax event if you just wait 12 hours. So suppose you're looking at an object in the sky, some star, and this is the Earth. This is the planet Earth. Now, in the morning, say at 5 a.m. At the time of sunrise, or yeah, maybe the sun is over here. So at the time of sunrise, you're looking at the star from position A. At the time of sunset, 12 hours later, you're looking at the star from position B. So you should expect the star to have slightly changed position in the sky. So there also you should expect some parallax. So coming back to why people believed in the geocentric model and the fact that the Earth seems to be at rest is because none of the stars showed any parallax at all whatsoever. So a star will show parallax if the Earth is moving, right? Because then you'll be looking at the star from different vantage points. So its apparent position in the sky should slightly change. So none of the stars showed any parallax at all. And so the smart people at that time had tried their best to see if there is any parallax shift of any of these stars or any change in the position of the star over the course of a year. They had not found any at all. And so that's why it seemed completely plausible to assume that the Earth must not be moving. And that's why the apparent positions of the stars in the sky does not change at all. So the most important reason why people of that time believed in the geocentric model, which says that the Earth is at rest at the center of the universe, was that the stars don't seem to show any parallax at all, right? But the real reason why they didn't see any parallax is because the stars are so incredibly far away. So the parallax angle that you would see for nearby stars, this parallax angle, is so insanely tiny that you need specialized equipment to be able to measure such an incredibly tiny angle. And so at that time, they had nowhere close to the technology to be able to measure such tiny, insanely tiny shifts in the position of a star. So that is the real reason why they didn't see any parallax. But they didn't know that. They just thought that there is no parallax because they just couldn't measure any parallax at all. So the most important reason why people believed in the geocentric model was that the stars never showed any parallax. Okay, all right. Is that clear? Does that make sense?
Yes, it does.
Okay, so it's 7 o'clock. I usually take a 5-minute break if I'm doing a live session. So let's take a 5-minute break, and it's 7 o'clock. 7:05 is when we'll resume. All right, so let's get started. So we talked about the geocentric model, and we talked about why people believed in the geocentric model. And I mentioned that the most important reason people believed in it was because the stars don't show any parallax. There were other reasons too, like we don't feel any uh, uh, strong wind blowing in the opposite direction, or all objects seem to fall towards the Earth, indicating that the Earth must be the center of the universe. So these were the reasons why people believed in the geocentric model. Now, I must also mention that not everybody believed in the geocentric model. There were some really smart people like Aristarchus, who had figured out that the Earth revolves around the sun, But because of Aristotle's influence, the geocentric model survived for 14 centuries. Everybody believed that Aristotle cannot be wrong. So the geocentric model survived for 14 centuries. Now, there's another reason why the geocentric model was so popular. Aristotle's theories over the centuries had become linked to the teachings of the Catholic Church. And so over the centuries, the beliefs of Aristotle and the beliefs of the Catholic Church sort of got intermingled. Um, and it seemed that Aristotle's beliefs were quite perfect for what the Catholic Church believed. So, for instance, the Catholic Church believed that the heavens are where God resides. So the heavens are the realm of perfection, right? The earth is where we live. It's not really perfect. Uh, the earth is not really perfect. But the worst place to be is underneath the earth, which is hell. So hell is absolute worst place that you can be. So above your head, you have the heavens, and then the earth is the earthly realm, and then underneath lies hell. And so that seems to line up with what Aristotle was saying, in the sense that you have the earth, which is the center of the cosmos. We live on the surface of the earth, which is not quite perfect. It's not quite a perfect place to be. Um, but hell is the center of the earth. So this is really, really bad over here. And as you go up towards the sky, you're getting closer and closer to the realm of God. So you're getting closer and closer to heaven, which is perfection, right? And so objects which are further out up in the sky are closer to perfection. So you would expect the moon or the sun or the planets to be these perfect orbs of light, uh, because they are closer to the heavens than we are. And so the closer you get to the heavens, the more perfect you become. And in those days, they had some ideas about perfection too. So the most perfect shape that you can have is a circle. The circle was believed to be the most perfect shape. And so that is why you'll see that in the geocentric model, it was believed that the Earth is at the center and everything is orbiting the Earth in a circle. Why did they choose a circle? Why not a square? It's because a circle was believed to be the most perfect shape. So if God made the whole universe, then how could God possibly choose a shape other than a circle? Circle was the most perfect shape. And the most perfect three-dimensional shape would be extension of a circle, which is a sphere. And so that is why the planets and the sun and the moon were imagined to be these perfect spheres or these perfect orbs of light. So yeah, so the most perfect region is the starry sphere, and the most imperfect region would be the center of the earth. That's what people believed, and it was in line with the teachings of the Catholic Church. And so the thing is that anybody who did not believe in Aristotle was also not agreeing with the Catholic Church. And in those days, it was extremely dangerous to not agree with the Catholic Church, because the Catholic Church had a tremendous amount of power over people's lives. And in those days, if you did not believe in what the Catholic Church was teaching, you could be arrested by the Inquisition and subjected to torture and death and all that stuff. So you did not mix with the Catholic Church in those days. Okay, so anyone challenging the Aristotelian viewpoint was not only challenging Aristotle, but also the belief in heaven and hell, which was what the Catholic Church was teaching. Okay, now in this uh, in this world where almost everybody believed in the geocentric model, and it was very, very firmly established in the minds of people, was born Nicholas Copernicus in the year 1473. So Nicholas Copernicus was born to a merchant family in Poland. He was orphaned at 10, and then he was raised by his uncle, who sent him to study law and medicine in college. So that's what he studied. After um, after finishing his studies, he took on a job as a canon in the Catholic Church, and he did this job for the rest of his life. So a canon is the equivalent of an administrative assistant. So that's the job that he did for the rest of his life. He was a very, very pious person, extremely pious person. All right. He was also very, very, very intelligent and tremendously interested in astronomy. Okay. Now, Copernicus was always troubled by this geocentric model because it just seemed so ugly and so horrendously complicated. You have the Earth, and then you have things orbiting the Earth in circles. Not only that, they're doing circles within the circles, and then smaller circles within the circles within the circle, so and so on. So he thought that this was a horribly complicated model, and so he was very disturbed by this. He in fact even said that if I was there at the time of creation when God created this, I would have suggested a far simpler model than this. And so he was tremendously disturbed by the fact that this model that people believe is so incredibly and so ugly and so complicated. So he thought that maybe there is an easier way to explain the motion of the planets in the sky. And he was aware that some people believed that the sun was the center of the sky, particularly Aristarchus that I talked about earlier, who nobody took seriously. So Copernicus took the idea of Aristarchus that maybe the sun is the real center of everything in the universe, and everything orbits the sun. He took that idea, and then using his knowledge of mathematics, he was able to put it on a very firm footing, and he came up with what is called the heliocentric model of the universe. So, or of the solar system, I should say. So in the heliocentric model, and I'm going to talk about that in detail in just a moment. So in the heliocentric model, why is it called heliocentric? Helios means sun in Greek, and centric. So that means in this model, the sun is the center, and everything orbits the sun, and nothing orbits the Earth except the moon. So the Earth and all the other planets actually orbit the sun. So this is the heliocentric model that Copernicus came up with. But Copernicus was very scared of actually publicizing these ideas, or making these ideas well known, um, because, as I said, in those days it was extremely dangerous to contradict the Catholic Church. And so he kept these ideas mostly to himself. He just discussed them with friends and people in his close circle. And it was only at the end of his life that his friends and acquaintances said that he should go ahead and write a book and explain these ideas so that everybody else could learn about them. And so he finished this book in 1529, but he only sent it for publication in 1542. So that is when he was on his deathbed. So that is the only time he felt confident, knowing that he would not be around for very much longer. That's the only time he felt confident to publicize his ideas of the heliocentric model. And he in fact died before the book was in print. So he did not get to see the tremendous revolution that his ideas brought about in the subject of astronomy, or in our understanding of the cosmos. So in the heliocentric model, the most important idea was the sun is the center of the universe. The Earth spins on its own and is only orbited by the moon. That's the only thing that orbits the Earth. And the other planets, and like the other planets, the Earth orbits the sun. So everything basically orbits the sun, and the only thing that orbits the moon orbits the Earth is the Earth's moon. Now, one amazing consequence of this very simple model and very clean model, in this model, you don't need to assume that there are circles within circles within circles and so on. So in this very simple and very clean model, one amazing consequence is that it's very easy to explain the retrograde motion of the planets. So let me just explain to you what retrograde motion is. And before I do that, since I do have a student, Ashley, have you ever heard of retrograde motion of the planets before this class?
I have, but I don't know how to explain it.
Yeah. So the reason you probably heard of it is because it's pretty common in astrology. People say that, oh, this is the period of Mercury retrograde, and you better be careful because Mercury retrograde is a bad time. So it's in the news. So that's probably how you might have heard of it. And as I mentioned earlier today, retrograde motion of planets means when a planet which appears to move backwards compared to the way it normally moves, right? So as I was saying now, it's very easy to explain the retrograde motion of the planets in this heliocentric model. So let me just quickly explain this, and then I'll show you a nice animation. I'll explain it with my hand-drawn figures, but then I'll show you a beautiful animation of this. So why do the planets appear to move backwards sometimes? Well, let's draw the sun here. This is the sun. And here is the planet Earth orbiting the sun. So in the heliocentric model, which is the correct model, the Earth and all the planets orbit the sun. All right, let's take any other planet like Mercury. Mars is probably easier. So here is Mars. Mars is also orbiting the sun. So here is the orbit of Mars. Mars has a larger orbit than the Earth. Okay, now Mars actually orbits at a slower speed than the Earth does, right? So suppose the Earth is over here in its orbit. Let's call this position 1.
I'm sorry to interrupt, but ever
Yeah,
since we
sure.
came back from our break, I can't see anything except
Oh,
yours.
okay.
Like,
Yeah, I forgot to share my screen, so so please remind me. I often forget
oh,
to do
oh,
that.
oh,
Okay,
oh, okay.
thank you
Thank
for
you.
reminding me. I'm really glad that you reminded me. All right, there. Okay, so
Okay, cool.
yeah,
Thank you.
so yeah. Suppose so. What I'll just draw this again. Okay, so all right. So here is the sun, and here is the Earth, which is orbiting the sun in a circular orbit. And here is, let's say, Mars. So Mars is also going around in a circle around the sun. It's orbiting the sun. But Mars has a slower speed. In fact, the larger the orbit radius, the slower the speed. So the Earth is orbiting the sun and Mars is orbiting the sun. Now, suppose the Earth is over here. So we are sort of approaching Mars, right? When the Earth is over here, let's call this position 1. So from position 1, we are sort of approaching Mars, right? So Mars will appear to be moving in one direction in the sky. But when we are in position 2 over here, we are lapping Mars. So Mars is going this way, we are sort of passing by Mars like that. So if you're on the Earth in position 2 and position 3, let's say, it will seem that Mars is sort of moving backwards because we are lapping Mars at that time, right? So to us, it would look like Mars is moving backwards. And so there are certain periods of time when we are lapping Mars. At that time, it appears to us as if Mars is moving backwards. It's very similar to when you're driving on the highway. So suppose you're on the fast lane going 75 miles per hour. Then when you pass a car, that's doing 65 miles per hour on the other lane, then after you've passed the car, it seems like the car is moving backwards. So that is why sometimes when we are lapping Mars, it appears that Mars is moving backwards. That's the simple explanation why the planets appear to have retrograde motions. Now let me just explain this with this simulation. All right. So in this simulation, you can see the big blue dot is the Earth, and the red dot is the red circle is Mars, and they're both going to be orbiting the sun. And in the window at the near the bottom right, it says view from Earth. That is what Mars will appear to be. That's what the sky will look like from the Earth, right? So in this simulation, you can see the actual motions of Mars and the Earth, and you can also see the apparent motion of Mars as seen from the Earth. So let's watch this. So you can see that Mars appears to be moving in a certain direction. But when we start lapping Mars, when we are passing by Mars, to us, it would look like, for a while, it would look like Mars seems to be moving backwards. From our vantage point, it would look like Mars seems to be moving backwards. And then after we have passed by Mars, once again, it will look like Mars is continuing to move in the same direction. So just when we are passing Mars, we're lapping Mars, at that time, it would look to us as if Mars happens to be moving in the opposite direction. So that is the true reason why retrograde motion happens. Does that make sense, Ashley?
Yes, it does. And I've
Yeah.
never seen that model before.
Right,
So
right. Yeah, yeah.
yeah.
So that is the whole reason why we have retrograde motion. All right. Okay, so you don't need, so you can see that this explanation is much simpler than the Ptolemaic explanation, which required circles within circles within circles and all that stuff. So this was an amazing consequence of Copernicus's model. There was a very simple and very intuitive explanation for why the planets have retrograde motion. So this was a very elegant model requiring none of the complications of the Ptolemaic system. And it was able to explain most observations. Now, let's talk about the whole reason why people were interested in these models. The whole reason is because people wanted to be able to predict the positions of the planets. That was the whole reason why they cared about these models in the first place. The most important thing the common people of the time wanted to know was that, okay, based on your model, can you give me a table which tells me where the sun is going to be 7 months from now, because 7 months from now, something important is going to happen in my family. And so I want to know the position of the sun or the position of Mars in the sky at that time. That's what people really cared about because they believed it played some role in their lives, the motion of the planets. So how good was Copernicus's model in explaining observations or in making predictions about the position of objects in the sky? Um, it was able to explain most of the positions of the objects in the sky with reasonable accuracy, but it turned out that it was not any more accurate than the existing Ptolemaic model, right? So the Ptolemaic model was also able to explain, in general, it was able to explain where Jupiter would be, where Mars would be, and all that. Uh, but it was not super accurate. It was generally true, but not super accurate. And Copernicus's model turned out to be not that much more accurate than the Ptolemaic model. So that is one reason people thought that there must be something wrong with Copernicus's model. And maybe it's just an interesting model, but maybe it's not true. The real thing is the Ptolemaic model, which people have believed for so long. And so the important point is that the Copernicus's heliocentric model, and I'll just write this down, Copernicus's heliocentric model was not more accurate in making predictions than the existing Ptolemaic model. Now you might be surprised by that. You might think that, okay, so this, we know from what we know now, this model is the true model. This is exactly what the planets are doing. So why would this not give more accurate answers than the wrong model, that the wrong Ptolemaic model that people used in those days? The reason is because there was a flaw in Copernicus's model. Copernicus, being a highly religious and devout person, could not give up the idea of circles. So like all the people in his time, he believed that God created the world and everything. So how can God choose any shape other than a circle? The circle is the most perfect shape. So he believed in his heliocentric model, he believed that the planets orbit the sun in perfect circular orbits, which we will see later is not strictly true. The planets don't orbit in circular orbits. So that idea is wrong. So that flaw in Copernicus's model was what led to the heliocentric model as discovered by Copernicus, giving not more accurate answers than the existing Ptolemaic model. So that is one of the reasons why people did not take it super seriously. Like they appreciated how simple this model is and how simply and intuitively it explains retrograde motion. But they realized that it's not more accurate than the existing model. So they thought that maybe it's just a curiosity. There's really nothing to it. It's just a curiosity. So as I mentioned, Copernicus did not feel confident or did not feel comfortable or secure making his model public, because he knew that he could get into a world of trouble if the Catholic Church realized that he's saying things that contradicts them. So see, he only sent his book for publication in 1542 when he was in his deathbed. So not a lot of people knew about this model, and also it was mostly ignored in his time. So he never really saw this model taking over the world while he lived. This model became much more popular later on at the time of Galileo. Okay. All right. Now, Copernicus's model was very elegant, but as I said, it could not seem to predict planetary motion with greater accuracy than Ptolemy's model. And Ashley, can you tell me why that is the case? We just talked about that, but I just want to make sure that that's clear. It's something I often ask on exams.
So what I'm understanding is that Copernicus's model was elegant, but because he could only see in circles, it wasn't able
Very
to show anything different.
That's exactly right. So that's exactly correct. So Copernicus could not give up the idea of circles. So in his model, he said that the sun is the center and everything orbits the sun. All of that is correct, but there was one big flaw. He said that everything orbits the sun in circles, and that's not strictly true, as we'll see later on. And so as a result of that, his model could not give more accurate results than the existing Ptolemaic model. And so this was, so I mentioned that in the next bullet point. So this was due to Copernicus's assumption that the planets follow perfectly circular orbits. Yeah, and so which is not true. Yeah, so the Copernicus's hypothesis was admired, but it was not accepted by people. And the slow process by which the Copernican hypothesis of the heliocentric model was gradually accepted is called the Copernican revolution. Okay, so we talked about this question. The main flaw in Ptolemy's model, okay, let's see. The main flaw in Ptolemy's model was that it failed to explain the retrograde motion of the planet. So do you think that's true or false? Was Ptolemy's model unable to explain the retrograde motion?
I guess it was not unable to explain it. It just was very complicated.
Yes, exactly. Very good. So it was able to explain it, but it was not the true explanation, and it was horrendously complicated. So the correct answer is that this is false.
Okay.
Ptolemy's model was able to explain the retrograde motion, though as we know, it was a horrible explanation and wrong ultimately. The heliocentric model assumes, what do you think is the answer here?
The fourth one.
Yes, exactly. Very good. Heliocentric means the sun is the center of the solar system. And I have one more over here. The heliocentric model was significantly more accurate than the existing model. What do you think?
So in its time, it would be false, but
Yes,
in reality,
exactly.
it's true.
Exactly. So it was not more accurate because of as we discussed earlier, it had one flaw. He assumed that the planets go around in circles. And so that is why it was not more accurate. All right. Now, the next person that we are going to encounter in the history of astronomy was this brilliant person named Galileo. So Galileo was an Italian mathematician and philosopher. Have you ever heard of Galileo before? That
Yes,
name?
I have.
Yeah. So he was an Italian mathematician and philosopher, and he was one of the smartest human beings that have ever walked on this planet. So he was up there with Isaac Newton. Very, 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 very brilliant person. Now, one of the amazing things about Galileo was that he knew, somehow, he just knew right from the time he was a little kid, that the way Aristotle and other philosophers of his time think about the world is completely wrong. So Aristotle's way of reasoning about the world was reasoning through first principles. So so they would just take some facts which they thought are self-evident truths. You don't need to prove them. And then based on those facts, they would use logical reasoning to construct more facts. So they believe that if the bedrock is true, the facts that you assumed are completely that you started with, if that is true and your reasoning is watertight, then anything that you derive with your reasoning has to be true. So that was called reasoning from first principles, and that is okay in philosophy and mathematics, but it just does not apply to the natural sciences. So in science, the correct way to think is to test whatever you're coming up with against experiment. You have to do experiments, and experiments are the ultimate arbiter of whether what you figured out is correct or not, right? So this is a no-brainer to us, but at the time of Aristotle, this kind of thinking was completely non-existent. And Galileo was probably the first person who believed that in order to really understand nature, the natural world, you have to use experiments to test your theories. And if your theories agree with experiment, only then you know that they're true. And if they don't agree with experiments, they're wrong, plain and simple. So Galileo somehow was born with that notion, and nobody else till him ever thought like that. So he was distinguished by a desire to perform experiments to test theories, and that was a completely radical approach at the time. Um, so Galileo was very, very brilliant person, as I said. Among his many discoveries, he made quite a few discoveries in astronomy, right? So, but I want to emphasize that astronomy was not we're only going to talk about his astronomical work, but astronomy was not the only thing that he worked in. He made many other contributions in physics, particularly. So in 1609, Galileo built a telescope. So he did not quite come up with the idea of a telescope. There was some people had come up with ways of building devices which would allow you to see further, like binoculars and stuff like that. But Galileo took those ideas and tremendously improved them and came up with the idea of a telescope, with which you could see objects out in the sky, right? So he built a telescope. He built the very first astronomical telescope in 1609, and he aimed it at the sky. And then when he looked at the sky, he realized that what people have been believing for 1500 years since the time of Aristotle is all complete nonsense. He was a very smart person, and he, even before he built his telescope, he knew that this whole geocentric model must be complete nonsense. And he knew that Copernicus's heliocentric model must be true. But once he built his telescope and looked at the sky, he realized it just completely hit him that everything people believed till that point regarding the cosmos is all complete nonsense. So he saw plenty of evidence for Copernicus's ideas. So now it's no longer just an interesting, Copernicus's heliocentric model was no longer just an interesting idea. He saw direct evidence that it is true when he looked at the sky. So first of all, he saw that the moon has mountains, valleys, and craters. This was in complete contradiction to what the Catholic Church and the geocentric model said. Remember, we discussed how in the geocentric model, the closer you are to heaven, the more perfect things get, right? And so the moon and the sun and the planets are these perfect orbs of light. So, but when Galileo looked at the moon, he saw that it does not look like a perfect orb of light at all. It has a bunch of mountains, valleys, and craters. Then Galileo studied the sun using his telescope, and he was able to see that the sun is also not a perfect orb of light. He saw that the sun has these big splotches on it, which are called sunspots. And then he saw not only that the sunspots move around, seem to be moving. If you're following a particular sunspot, you'll see day to day that it's changing position on the sun, which tells you that the sun is spinning just like the earth is spinning. So it's not this perfect orb of perfection, this perfect orb of light that's sitting in the sky, that's rotating around the earth. It's spinning just like the earth is spinning, and it has these ugly splotches on it. So then when he looked at Jupiter, that is when he saw the most convincing to him, the most convincing piece of evidence that the geocentric model is just complete nonsense. Because when he saw Jupiter, here are some actual diagrams that he drew over here. This is actually Galileo's handwriting. So this is an image from his diary, and he has written down the dates over here. These numbers are dates in January 1610. So this is 7th of January 1610, 8th of January 1610, and this big circle that he draws is the planet Jupiter. And what do you think these little dots are around that he's drawn? Do you have any idea, or can you guess?
I guess they're the moons.
Yes. So he didn't know what they were, but to him, at that time, people had no idea that other planets can also have moons. Um, but he saw that he saw the positions of these dots change. So you can see that the diagram that he's drawn for the 7th of January has the dots like this. The diagram that he's drawn for the 8th of January has the dots like this. 9th of January, they look like this, and so on. So by noting the positions of these dots, and notice that, remember that he had no idea what any of this was. He knew that the big thing was Jupiter and the others were just little spots of light. But by noting how the spots of light changed position from day to day, he realized that these must be orbiting Jupiter, right? And so that is why some of them just disappear. Like, for example, if my head is the planet Jupiter, and and my hand is a moon of Jupiter. So sometimes, if when the moon of Jupiter goes behind Jupiter, then you won't be able to see it, right? And then it'll come out on this side, you'll see it. So okay, so that's what he noticed over here, that these things are sometimes disappearing behind Jupiter and then reappearing on the other side. And so by studying that and being an insane genius, he was able to figure out that these smaller objects are actually orbit around Jupiter in the same plane that we are looking at, in the same plane as the ecliptic. And so he realized that Jupiter seems to be a mini version of the solar system. So here is Jupiter at the center, and there is stuff that's orbiting around Jupiter, right? And that is completely against the teachings of the geocentric model, which says that the Earth must be the center of everything, the most important part of the universe. Everything, the Earth is the center of everything, and everything, including the sun, goes around the Earth. That's what the geocentric model says. But here he saw that that's not true at all. It seems that Jupiter is like a mini version of the solar system with stuff that's orbiting Jupiter. And so once he saw this, he was absolutely 100% convinced that the geocentric model was all complete nonsense, and the heliocentric model must be true. And then there was another thing that really struck him, but not as much as the moons of Jupiter. He saw that Venus has phases just like the moon. So in the video that I put up for Thursday's lecture, I explained why the moon has phases. So I spent some time, I showed a nice video with an experiment that showed why the moon has phases. Um, Venus also has phases. So to the naked eye, Venus looks like just a dot in the sky. But if you look at Venus with a pair of binoculars or a telescope, then you will be able to see that sometimes it's in its full phase, or sometimes it's in its crescent phase, and so on. So Venus has phases just like the moon does. And that is only possible if Venus's orbit is inferior to the Earth's orbit. So the only way that Venus would have phases is if this is the sun, here is the Earth's orbit, and here is Venus's orbit. So if Venus has an orbit like this, it's orbiting the sun, and its orbit has a smaller radius than the Earth's orbit, that's the only way that Venus can have phases. In the geocentric model, it would be impossible for Venus to have any phases. So using his telescope, he looked at Venus carefully and tried to see if Venus had phases, and he saw, yes, it does have phases, which shows that the geocentric model cannot be true. So the two most convincing pieces of evidence that Galileo got, which convinced him that the geocentric model is true, was the moons of Jupiter and also the phases of Venus, but he saw the phases of Venus much later. Actually, I believe it was suggested to him by a friend saying that if the geocentric model is true, then Venus will never have phases. And so he said that, okay, I'll go ahead and check if Venus has phases or not. And he found that it does have phases. So he saw this one later, but what struck him most of all was this, that that Jupiter has moons. That is what convinced him that the geocentric model must be complete nonsense. So this is a question that I sometimes ask on exams and quizzes, that of all the things that he saw with his telescope, which struck him most of all, convincing him that the geocentric model is wrong, and the correct answer is the moons of Jupiter. All right. Now, so another planet having moons provided the strongest support for the Copernican model, which is that the Earth wasn't the center of everything in the world. So the fact that Jupiter has moons clearly proved that it's not correct to say that the Earth is the center of everything. Also, the phases of Venus could only be accounted for in the heliocentric model, as I just mentioned. So after Galileo saw all this, he wrote this little book called Sidereus Nuncius. Sidereus Nuncius means messenger from the stars, in which he detailed all his observations, and he challenged the religious dogma. He detailed all his observations, and that book obviously challenged the religious dogma and the orthodoxy in his time. Um, and so this book started becoming very popular, and people started realizing that, wow, it's amazing. So everything that we knew about the world is actually wrong. The Earth is not the center of everything; it's the sun that's the center of everything. Uh, so as his ideas started getting more and more popular, the Catholic Church started taking note of that, and in 1616, the ideas were judged to be heretical by the Catholic Church, which is very, very dangerous. So the Catholic Church decided to take action, because Galileo's ideas were getting more and more popular, and more people were getting the idea that the church had been teaching us the wrong thing this entire time. And so they judged his ideas to be heretical, and they decided to, and the Catholic Church banned Copernicus's book. Remember that Copernicus had written this book in which he sent for publication in 1542, and died before that book was in print. Now, in those days, highly knowledgeable and educated people like Copernicus would write books in Latin, which was a language that only the highly educated people could understand. It was a very difficult language, but the commonly spoken language was Italian, and most common people couldn't just spoke Italian, and they couldn't understand Latin unless they went to the university and stuff like that. So Copernicus wrote his book in Latin, but even when it was published, not a lot of people would really be able to read it or understand it because it was in Latin. So one of the things that Galileo did was that he translated Copernicus's book in Italian, and republished it, so that a lot of people could understand Copernicus's work. And that is how Copernicus's work and also Galileo's observations started getting really popular. But in 1616, the Catholic Church, as I said, decided to sort of stamp down on this, and Copernicus's works were banned by the Roman Catholic Church, and Galileo was ordered to quit astronomy. In fact, I've read books on the history of this, so it's interesting how in those days, if you had a copy of Copernicus's book, then what you had to do if you owned a copy of the book was you could either throw away your copy, or you could correct certain parts of the book. So you were given a list of corrections, and so you would have to take your copy of the book and scratch out those paragraphs and basically replace it by what the church wants it to say. So you could either do that, or you could throw away your book. But if you got caught with an unedited version of the book, you'd be in very serious trouble. All right, so so that kind of damped Galileo's efforts when the Catholic Church stepped in and ordered him to quit astronomy. So now in 1629, so this happened in 1616. So in 1629, 13 years later, there was a new pope. And the new pope was actually a friend of Galileo. And so Galileo thought that now is an opportunity to again push these ideas a little more, make them popular. So he published a new book on Copernican ideas, which is called Dialogue Concerning Two Chief World Systems. So that was the name of the book. So he in fact got permission from his friend, the Pope, to publish this book. And in this book, the way he wrote this book was that instead of just writing a dry textbook, what he did was he had three characters in this book. And so the book was a debate among three friends. One of them was Salviati, who was a defender of Copernicus. And then this is really Galileo himself. There was another guy named Simplicio. You can tell from his name that he's not very smart, and he is a dim-witted defender of Ptolemy. So he will just say that Ptolemy is always right, and he's too dumb to consider any evidence or any arguments. So he's a dim-witted defender of Ptolemy. And then there was this other character in the book. His name was Sagredo. He was intelligent but uninformed. So Sagredo was somebody who was smart enough, who did not have the knowledge that Salviati had, but he was smart enough to critically examine evidence and arguments and make a decision. So he would say that, okay, this is what I have always believed, but looking at all this evidence, I have to change my mind and accept that this is true. So he was somebody in the book that had the intelligence to do that. So the whole book is this delightful debate among these three characters. And so this is how he wrote the book. And he put out these ideas of Copernicus brilliantly in this book. Now, I told you that he took permission from the Pope of the time, who was more liberal, and in order to publish this book. Now, the Pope said that, okay, you can publish this book, but you have to put my personal views in the book as well. And the Pope's personal view, which he required Galileo to incorporate in his book, was that maybe there is all this evidence that Copernicus's ideas are true, but maybe that's just part of the will of God. So what we've been believing so far from Aristotle's time, the geocentric model is really the true model, but maybe it's just part of God's plan that all the evidence that we find seems to contradict it. And so maybe we just need to live with that contradiction. So that something like that was the Pope's personal viewpoint. And he wanted Galileo to include his personal viewpoint in the text, in that book. Now, Galileo said, okay, I'll put that in the book. But what he did was he made that one of the arguments of Simplicio. So Simplicio, the dumb villain of the book, says the thing that the Pope wanted presented in the book. And
That's
so naturally,
so silly.
Yeah, so the Pope looked like a complete moron in the book because his words are coming from Simplicio. And so naturally, it was hilarious. And the Pope looked like a complete fool. And once the Catholic Church realized that that this book was so popular, and Galileo has actually made the Pope look like a complete idiot in this book, they were furious, as you can imagine. And so the Inquisition, which I've talked about before, the armed wing of the church, decided to step in and said that enough is enough. We need to just completely stamp this nonsense out. And so yeah, and Galileo's book had completely sold out in a few months. It was extremely popular. So the Inquisition stepped in. Galileo was arrested, and the church forced him under threat of torture to retract his views. Yeah, so the church said that he needs to publicly retract all his views and say that everything that he has said so far is wrong. And he was also placed under house arrest for the rest of his life. That was his punishment. So yeah, so that is the story of Galileo. Interestingly, in 1992, the Roman Catholic Church publicly forgave Galileo for his crimes. And I remember this, I was a kid at that time, but I remember in India, I remember it was in the news, and Pope John Paul II was the Pope at that time. And it was in the news how he publicly forgave Galileo 300 years later. So, so that is the story of Galileo. All right. Now, let's look at this. So who published the first astronomical observations made with the telescope? Very easy. So who do you think?
It would be Galileo.
Yeah, exactly. Galileo's initial observations was most challenging to establish. Which of them was most challenging to establish geocentric beliefs? Do you think?
I guess, is it the moons of Jupiter?
Yeah, exactly.
Is that what we're saying?
Yes, exactly. So that's the one that struck him the most and convinced him that the geocentric model is all wrong. And okay, so that is the story of Galileo. And now, eventually, people did realize that the geocentric model is wrong and the heliocentric model is correct. The Earth revolves around the sun, but there was still one very big problem with this in the minds of people at that time, which I've mentioned before, is that there is no parallax. So I told you how if the Earth is rotating around the sun, if it's in orbit around the sun, then some star which happens to be nearby should show parallax. So, but people had studied every possible star as I mean, to the best of their abilities, and the positions of the stars in the sky never seem to change. But they should. If the Earth is moving around like this, then your vantage is changing, right? So you should see the positions of the stars change a little bit, but they never found that to happen. And so that is why it was very difficult for people to accept that the Earth must be moving, because then the immediate next question is where is parallax? So some stars should show some parallax, but none of the stars had ever shown any parallax. So there was really no evidence, no direct evidence that the Earth was going around the sun. The first direct evidence was obtained in 1728 when a person named James Bradley noticed that the positions of the stars do change a little bit at different times of the year. In 1838, as late as 1838, so 200 years after Galileo, was the first time that the parallax of a star was actually measured by a person named Friedrich Bessel. So he was studying a particular star named in the constellation Cygnus, and he had designed a very clever experiment, and he found out that the position of that star in the sky does change a tiny little bit at different times of the year. So the stars do have parallax, but it's so small that it's very difficult to measure. And that is the reason it had never been measured before. So, so it was only in 1838 that the first parallax of a star had ever been measured. So till then, there was really no evidence that the Earth is really going around the sun. Okay. Now, of course, we have overwhelming amount of evidence, like we have sophisticated data, we have space probes and all that. So now there is no doubt about the fact that the Earth is orbiting the sun. But it was not till 1838 that we had direct evidence that the Earth is moving around the sun. All right. Now, around the same time as Galileo, there was a person named Johannes Kepler, who was another giant, intellectual giant in our study of the history of astronomy. So Kepler was the same level, intellectual level as Galileo, insanely brilliant. He knew right away that the geocentric model must be wrong. He'd figured out that Copernicus's model, heliocentric model, must be correct. And so his groundbreaking discovery was what clarified our understanding of the motion of the planets, right? Now, Kepler was actually an employee of another brilliant astronomer named Tycho Brahe. So it's pronounced Tycho, Tycho, but the correct pronunciation is Tycho Brahe. So he was an employee of Tycho Brahe, Tycho was a very interesting character. He was the imperial mathematician of the Holy Roman Empire. So Tycho was born to an insanely rich family, one of the richest families of that time. So he was just absolutely loaded, extremely, extremely rich his whole life. And he was also very brilliant, and very temperamental. So it's believed that it's not believed, it's known that he when he was in college, he had an argument with one of his classmates over, of all things, who's the more brilliant mathematician. And so they decided to resolve it with a duel with real swords. And the mathematician chopped off Tycho's nose. And so Tycho's family built him a nose made of gold, very, very expensive. And in fact, not just one, he had multiple noses which he could just sort of put on his face. And so he used different noses for different occasions. So he had prosthetic noses, basically. And so Tycho was insanely brilliant. And Tycho was really interested in trying to understand the motions of the planets as accurately as possible. So Tycho built this observatory where he had, so here is a painting of Tycho in his observatory, where he would take the best possible measurements that you can without a telescope, naked eye measurements. So he had all sorts of clever equipment with which he could figure out the positions of the stars, of the planets in the sky. And so he collected very, very detailed measurements of the positions of the planets in the sky for many, many years. Because in order to really understand the motions of the planets, it's very important to know their positions in the sky as accurately as possible. And so that's what he was trying to do. So he collected this enormous amount of data over a few decades. And Kepler was one of his employees. Kepler was actually completely opposite, polar opposite to him. So Kepler was a humble person. He was also super brilliant, and he also came from a very poor background. So he grew up in poverty, complete poverty. He was also tremendously interested in astronomy. So he was very happy to get a job as a technician in Tycho's observatory. So Tycho soon realized that Kepler is insanely brilliant. And when Tycho died, he died very young, at the age of 32 or something like that, he died. And so when Tycho died, he made Kepler, Kepler became the director of the observatory, even though Kepler was just a lowly technician at the time under Tycho. Kepler became the director of the observatory. And Kepler got hold of all the data that Tycho had collected, right? And so after Tycho's death, Kepler inherited his position and his data. So Kepler had already accepted the heliocentric model, as I mentioned. And what he was trying to do was find a simple description of planetary motion that would fit all the data that Tycho had collected. So he had all this data of where Mars is today, tomorrow, 3 months from now, 6 months from now. So there's this huge amount of data of the positions of all the planets over years and years and years. So you can imagine it's extremely dry data, just books upon books in which you have the date and the time and the position of Mars and all the other planets written down. So he wanted to find a particular model. A model is basically a conceptual understanding of what exactly are the planets doing in the sky so that their positions will match with the data that has been collected. So that's what Kepler was trying to figure out. So after a lot of effort, a humongous effort, almost 29 years of effort, and many false starts and blind alleys, he came up with a set of 3 laws which bear his name, and these are called Kepler's laws. So these Kepler's laws are the true understanding of how planets orbit the sun, how planets move around the sun. So that represents the correct understanding of what the planets are exactly doing. And once you have Kepler's laws, you can perfectly explain the motion of the planets in the sky, and you can make perfect predictions. You can say that, okay, 6 months from now, Jupiter is going to be in that part of the sky in the constellation Sagittarius or whatever, and you will find Jupiter over there. So Kepler's laws represent the best description, the most complete description of the motion of the planets in the sky. So I think we're just going to stop here today. And in the next lecture, we'll discuss Kepler's laws.